Okay. All right. So welcome back, everybody. So we're going to have Masoud Kamgarpour from Queensland speaking about towards Katz's polynomials for reductive groups.
Thanks a lot for having me. It's great to be here, and great to be also reunited with Travis. Travis and I go way back, almost 20 years ago. We have lots of stories, so if you want to hear some of that, then you have to come for a drink with us later. But today I want to tell you about Katz's polynomials for reductive groups. So this was a little fun project that we did with my students, David, Nam, and Stefano, who have all now graduated and are off to doing better things. And so we're going to take a sort of a non-direct path to Katz's polynomial, so I'll get to that later. And the path we're going to take is using character varieties. So I'm going to start with we're just giving a definition of what is character variety. So let me start with that. So definition of character variety. And this is a topic that, of course, Travis has also worked on, character variety. So perhaps some of you have heard me talk about that, but I will remind you of all the necessary definitions. So I will take G to be a connected reductive group. So these words are not, you can think about, for instance, GLN or SLN or SPN or SON, or if you're more adventurous, you can think about E8. And I'm going to fix conjugacy classes. G. And I'm going to consider a n-punctured genus G surface. And I'm going to look at the character variety associated to this data. Okay. Now, maybe before I move on, let me just make a couple of comments about restrictions. First of all, so the character variety is going to be associated to the pi1 of these. So let's recall that pi1 of these is generated by, it has a presentation of this form, subject to one relation. And so I will define character variety in a minute, and it's just basically modular representations of pi1 into G, where the loops around the punctures, the i's puncture goes into CI. Now, of course, one could consider this for any algebraic group, not necessarily reductive, and that's actually interesting, but we know a lot less about the non-reductive case. I'll make a bit of comment about that later. And one could also consider not just surfaces, but actually any manifold that is pi1. And again, we know a lot less about what happens to character variety in that case, except we know some things when for three manifolds. And when G is SL2, then there's a lot of work on that character variety. So people like Colin and Shell, they worked on this, but from a different perspective. So today we will mostly think about the arithmetic geometric aspects of the story. Okay, so let me define for you what we're dealing with. So let R be the set of homomorphisms such that then G acts. So first of all, R. So this is the same as giving tuples in the group times these conjugacy classes satisfying the commutation relation. And you see this description tells you that this is an algebraic variety because this product of g to the 2g times c1 times cn, that's clearly a variety, and this is a polynomial equation. So that cuts out, scheme. When I say variety, I just mean a scheme of finite five, okay? So this is an algebraic object. This is called the representation variety. And the group G acts on this by just conjugating all of these. So the action of G from here. The quotient x equals r divided by d is called the character variety associated with this theta. And anytime in math one talks about quotients, one has to be a bit careful what kind of quotient are we taking. So here there are two choices. We can take the stack quotient or we can take the GIT quotient. But I'm going to actually assume in my talk that these conjugacy classes are chosen in a generic position. So, and if you assume that, let me not be too specific about what generic means. This is the usual sort of thing from stability conditions. So if you assume these are these tuple is generic, then the action of G on R has finite stabilizer. And so therefore, in this case, actually the stack and the GIT quotient are very close together.
Sorry, I'm not sure if the physicists know actually what stack and GIT quotients are.
Yeah, actually it doesn't matter. So that's what I want to say is that with this generic assumption, then it's like whatever quotient you want to consider. Whatever the notion of quotient you have in mind will work. Okay? So that's the point of that's the point of assuming generic, then actually you don't need to worry about what quotient really means.
Probably the one they have in mind is GIT, but you might not know that's what it's called. But
yeah,
the one that gives you usually a singularity.
If it has finite stabilizer, you might as well think about orbit spaces. It's almost the same, up to a finite thing.
Right. So because of the finite stabilizer, that means it's not going to be in any event, even if you take the GIT quotient, you're expecting to get a stack then.
Or you get orbital in physics.
Yeah, when orbital in physics could mean the cone, the singular thing, or it could mean, I guess.
Yeah, this could have singularities actually. It has orbital singularities. Yeah.
So like for non-generic, it's an artin stack, not
for non-generic, it's either an artin stack if you consider the static quotient, or if you can take the GIT.
Okay.
And what the singularities will then be more severe than just orbital.
Okay, and they come the Lemma form.
It won't be the Lee-Mumford anymore. It's not generic.
Okay.
But if it's generic, it's the Lee-Mumford.
The Lee-Mumford stack, or it's just a singularity. You could think of it as a singular scheme, and then they're not the same, then obviously. But
no, but actually, for instance, we're going to count points over finite field, and the number of points will be the same.
Oh, I
will explain.
So for the counting problem, you don't care which one you take.
Yeah.
Okay. All right.
Great. Any questions? Comments?
Like in GIT, like you consider like a character, like as a stability condition.
Good question. What I say here, I mean the trivial character. The GIT with respect to trivial, so the spectrum of the invariant ring.
Okay, so it's better of E1.
Why? Because actually we don't. This is an important point. This G might not have any character.
Yeah, that's right.
Right, because G could be semi-simple.
All the ones on your list except for the GLN will basically be like that.
Yeah. Yeah, and this is actually a point that maybe we return to later. There is a conjecture at the end that exactly this point makes it hard to prove. So we'll
Okay, so
we don't have this flexibility of the character.
yes, it's really a different deformation that like just changing the character.
Yeah, changing the character would, yeah, sometimes they call that the twisted GIT quotient, but yeah, because GIT quotient with respect to a character or just the ordinary GIT quotient.
Yeah. Okay, let me talk a little bit about the significance of this space in oh. So let me talk about mathematical significance, and then we'll talk a little bit about what people in math physics also, how they think about it. So an important first theorem is that this so by the way, this is also called the Betti moduli space. So this is also denoted by I will write it as AKA, sometimes denoted as M Betti and called the Betti moduli space. And I will talk about why Betti moduli space. So and if I want to emphasize that I'm attaching it to a group G and surface sigma, I write it like this. So first result is that this is isomorphic to moduli of connections on G bundles on sigma, or what physicists call gauge classes on the Riemann surface. And this is known as the Riemann-Hilbert correspondence. And it's an isomorphism of complex analytic manifolds. Okay. So this is intimately related to connections on our space. Then another result that's called the non-abelian Hodge theory, and also this is an explicit isomorphism actually. The map from here to here, this is called monotony. So that's an explicit map. There's a second isomorphism that goes from these to moduli Higgs bundles on sigma, and this is known as the non-abelian Hodge theory. And sometimes people also combine it with two isomorphisms and think about non-abelian Hodge as isomorphism between these two spaces. So remember, this is called M Betti. So let me also tell you some of the terminology. This is called M Deram, and this is called the Dolbeau modular space. In case you've heard these words, if not, don't worry about it. So, and this is a real analytic isomorphism that's really hard to actually. There's no map. So this is first of all something that makes it hard. There's no explicit map between these two things. It's proved by difficult PDE, proving that certain PDEs have solutions in the sort of style of Yau's proof of the Calabi conjecture. So that's sort of the kind of maths that goes into these. You know, when I was a student, and for many years after that, I sort of believed that analysis was nonsense. And so I couldn't understand the point. You know, this circle of idea really sort of drove home to me like why analysis is useful and beautiful. Because really, you really need analysis here to make this work, and it's really a beautiful story. What's interesting is that it's a real analytic manifold. So what's happening is that you have one manifold, and you have three different algebraic structures on it. Okay, that's also a strange sort of a situation. Usually, when we think about usual algebraic varieties, there's sort of one canonical manifold structure there, but and vice versa. But here, the situation is different. So there's manifold with many different realizations: the Betti realization, the Deram, and the Dolbeau realization. And all of this sort of arose from moduli space. So the unifying thing here is actually moduli space of solutions to Hitchin's equation, which is actually what sits in the center here. So maybe I will put it here, and Hitchin which is the central object here. This is solutions to Hitchin's equations, which is a two-dimensional version of Yang-Mills equation. Okay, so Hitchin sort of used this technique of dimensional reduction to go from Yang-Mills, which is defined on R4 or the 4 manifold, to a two-dimensional version, and he looked at the solutions of that, and he came up with this manifold, which has, then he noticed, has a very rich geometry with different realizations. Okay, so I sort of love this space because it's a kind of like a nice illustration of unity of maths. Basically, any kind of geometry that you may be interested in, differential, Riemannian, mathematical physics side, algebraic, is sort of present in this picture. Okay. So maybe I mentioned a couple of more points of significance of this space. How I arrived to it was from Langman's duality. So maybe before I go there, any questions about this picture?
Did you say what these isomorphisms, what properties isomorphisms have, or that's not relevant for you?
I think
They're bijections.
I said that this is the complex analytic isomorphism and this is the real analytic isomorphism.
Okay.
Yeah, and that this is given explicitly by monodromy, but there's no explicit map here, as far as I know. Yeah, I think we can discuss that more if you have a question, but probably that's for motivation. This is the motivation part of the talk, so I think that's probably sufficient.
Okay.
Question.
Yeah.
The left upright, is it a space of all connections on the
On G bundles, on
G bundle?
Yeah.
Can I say it's the space of all connections, like then portion by G, like construction of such moduli space of connections?
Oh yeah, isomorphism classes.
Okay.
Yes. So yeah, we do quotient 5. Yeah. The isomorphism classes of. Yeah.
Okay.
Everywhere also heat bundle. Yeah.
Okay.
And here you see we divide by G, and that's because we're considering isomorphism classes of representation.
Okay.
Yeah.
Judge a space of connection, it has a complex algebraic structure or it's just complex analytic?
It has a complex algebraic structure.
Okay.
All three of them have complex algebraic
Okay,
structure,
the judge that it's complex analytic.
but they're different.
Like,
These two have different complex analytic structure. All three have different complex algebraic structure.
okay.
These two have the same complex analytic structure, but
Okay.
these two are different. Yeah.
Because like in the model, you have some kind of exponential thing.
Yeah. So this M Hitchin, another way of thinking about this is that you have a hyperkähler manifold. So there's actually a P1 worth of yeah, there's a hypertelemetric, and yeah, I have been talking about those, but yeah.
Hyperkilometric on the smooth
Yeah.
levels.
Okay, so maybe another point of significance was that, I mean, if you want to summarize Langman's duality in one, geometric Langman's duality in one sentence, then this is what it would be. It would say that this xg, so this space that we're talking about, the character variety, there's somehow a duality. So let me say Langman's duality aims to geometric aims to establish a duality between character variety like this and draw with different colors to distinguish from the above, and G-check bundles on the surface. So moduli of G-check bundles on the surface. Okay, so that's sort of the heart of the geometric Langman's duality, is that there is a dual group to G. So for instance, the dual of SP2N is SO2N plus 1. Okay, dual of SLN is PGLN. So there's a dual group, and modular representations of pi1 here is in duality, some sense, with moduli of G-check bundles on sigma. So this is a duality between two sides. So This character right that we're discussing is essentially the central object on one half of Langmuir duality. Okay. And another important place where this comes up is the mirror symmetry, which suggests that there should be a duality between character varieties between dual reductive groups. I mean, this is the Betty version. There's also a version for the connections and Higgs bundle. And some of these have been proved. For instance, for Higgs, this was conjectured by Algebra and Tedious and then proved by Brokening and Weiss and Ziegler. Yeah, so it kind of comes up, this space comes up with all sorts of different applications and areas of mathematics, the character varieties. All right, so that's what I wanted to say in terms of significance. Any questions? Comments?
So mirror symmetry relates the G and the G check also, you say?
Yeah, that's well, supposedly that hasn't been proved, except maybe in SL2 PGL2 case.
So what's the statement there?
Well, for instance, that that the stringy cohomology of this should be the same as the stringy cohomology on the dual
Oh,
side. In this overflow technique.
they're not isomorphic, but they have the same stringy cohomology.
Yeah, yeah.
And then what about the geometric Langlands duality then? You say that? What's the?
Well, that, I mean, one statement is that coherent sheets here, the category of coherent sheets here should be the same as category of Kamgarpour sheets here.
Oh, right.
Yeah.
There we're looking at the coherent sheaves on this thing. And the mirror symmetry, I guess also you could have stated there's an equivalence of categories of coherent sheaves or something like that, the derived
I
category.
think, yeah, I mean, the version I gave was the four-man's mirror symmetry, the topological mirror symmetry, but that, you know, they have Konsevich's version, like the higher
derived
category.
equivalence.
But like that hasn't been at all proven in any case. So
I see, okay.
at least in this topological mirror symmetry with the stringy numbers, that has been proven in some cases, especially in the Higgs setting. But the Fukaya category of, for instance, Higgs bundle is not, I don't think.
It should be from the A side on one to the B side on the other, but then the stringy cohomology you can define, it doesn't depend on whether you're doing A or B side. Or...
Yes, that seems to be that some simplification on that.
I see.
Yeah.
All right, I don't know anything much about though. Okay. That's fine.
Other questions or comments? How are we doing on time, Charles?
Oh, it's 11:24, we're fine.
24. Good. All right, so I mean, people study these character varieties from many different perspectives. So when I write goal here, let me just say, in my little world, you know, this is or sub-world, and nearby, what is the goal? Or at least say something that would be relevant for this talk. And that's, so one important goal is to understand geometry and topology. Topology of character varieties. And this can take many different versions. It could mean that understands cohomology groups, you know, Betti numbers. It could mean understanding the metric on it. It could mean understanding singularity. It could mean understanding many different things. But here I want to sort of concentrate a bit more in understanding cohomology of this space, which cohomology is a way of linearizing the space to get some vector spaces. And we want to know, for instance, what is the dimension of these vector spaces. And maybe you want to ask some finer questions, like, for instance, what is the they didn't define the notion of mixed Hodge structure on cohomology of a complex variety, so you might want to know what are the mixed Hodge structure. So let me just say a few words about the state of the art. That a lot is known. A lot known in type A. What do I mean by type A? I mean if G, i.e. if G is, for instance, GLN or SLN or PGLN. Okay? A lot is known in these cases. This is due to the work of many people. For instance, Alville, Viegas, Letlier, there's many, Schiffman, Mellit, and many others. But little is known beyond Python. So if you were studying, for instance, representation theory of finite reductive groups, like the situation is similar to like 1950s or maybe 1960s, where people understood what the representation of GLN over SQ looked like. That was the work of Green, but then it had to wait for Delin and Lustig to sort of completely revolutionize that field using tau cohomology. And give a uniform understanding for all reductive groups. So the situation is similar. So we know a lot about GLN, SLN, PGLN, but very little beyond that. So that's what gave rise to this project. We were trying to see if we can go beyond type A and say something about general reductive groups. Okay, so that's
But these correspondence here is known in this case.
yes, the correspondence is known. So when I say this is known, I mean about the cohomology of this case. Yeah, these are it for general G, general reductive G.
And even the punctures, everything.
Yes, even the function. Yeah.
Okay.
Yeah, this was already figured out by well, to a large part by Simpson.
Right.
Yeah, I mean the important names here is Simpson, Kitchen, Corlett. These are the people that sort of work on feature. This was already sort of late 80s, early 90s. This computation of cohomology, this is sort of like 2010 to 2020. That's yeah. Question?
Yeah, has it something to do with the choice of cohomology theory, like those three you write in the right-hand side?
Yeah, I mean, does it have to do with choice of cohomology theory?
Yeah, as you mentioned here, they're like three type of moduli space.
Yeah, but underlying manifold is all isomorphic. So, for instance, the singular cohomology is the same for all of these objects.
Yes.
But the mixed Hodge structure changes. So, for instance, this is pure, and this is pure, whereas this is not pure.
Yes.
I guess you know what
like some comparisons, like from other expert structure on the
yes, that's it.
Those three things.
You might have heard of the P equals W conjecture. That has to do with the comparison of the mixed Hodge structure here, so that there's a non-trivial weight filtration, and then the question is what is the corresponding thing here, and that's the perverse filtration. Hence the P equals to W, perverse equals to weight. That's if you've heard of these words. Yeah, it becomes more complicated and finer information yet. Can talk about that as well.
But you think that something like that holds beyond type A?
Oh, yes,
P
it has to. I mean, our result also provides some evidence for that. Yeah.
But none of these methods is like these two different proofs of this P equals W, none of these methods apply to the beyond type A case.
I talked to the Sasha Minette, who worked on one of them, and tried to see if we generalize, but there's some bottlenecks that need to be resolved first. It wasn't clear. I don't know the Davish and the other proof. You would have to ask them. It wasn't obvious to me how to generalize it, but you know, I'm not an expert on that group, so it's
Okay. I know that they've generalized this to some various settings or something, but I guess it doesn't include.
well, yeah, they generalize it from GLN to like SLN. I think it's all type A. I've never seen anything beyond type A. As far as I know. And certainly there's nothing out of form of like for uniform and reductive groups, you know, which is really what you want. That's it. You don't want type by type analysis somehow. The statement, I believe, holds uniformly in reductive groups. So, you know, you want some, yeah. Okay.
Okay. Yeah, go ahead.
So, yeah, so this what gave rise, so let me say, this was our starting point. We wanted to see if we can go beyond type A, say something about general reductive. Okay. And let me also say that the key technique for computing cohomology that everybody uses in this field, and we also use as well, is the wave conjecture, which are of course proved. And in a sentence, wave conjecture, what that allows you is that, so this says that counting points over finite fields gives information about cohomology. So let me be slightly vague about what I mean. For instance, I can just say if your cohomology is pure, then actually counting points will give you somehow the Betti numbers. But if it's not pure, then it gives you something called the E polynomial, or it's polynomial count, but it gives you information. That's what the wave conjecture says. And that's somehow in many cases of moduli spaces, that seems to be one of the only ways to come to access cohomology. Even though counting points doesn't seem like an easy task, that seems to be the only way to, for instance, this is this seems to be true in this type A case. That's the only way that people have been able to compute cohomology was by counting points. Okay. And so let me write important open problem. Is compute, if you want to be a bit more specific, is compute mixed fudge structure of this category. And this actually is even open for type A still. So there's conjectures of Hausel and Viegas about how this fudge structure should look like, but that's hasn't been proved yet. And yeah, so that's what I want to say in terms of overall goal and sort of what is known so far. Questions or comments?
Yes, when you care about like quantify your finite fields, you refer like to really like programming like computer programs that really like put the part, or more like using motivic techniques on the motivic decomposition from the space.
More actually sometimes you have to do both.
Okay.
Yeah. If you just computer cannot just randomly count points. You have to put it in a form that the computer can understand, right?
Okay.
Yeah. So you have to sometimes do first that motivic decomposition or something related, and then you can put it in the computer to see what kind of things you get. You know, that's yeah. So both, I would say, and actually we do both. We do somehow a kind of motivic thing, and then we'll put it in computers to actually get a explicit thing out.
Motivic things like don't suffice, like you really need to.
Well, motivic things give you kind of an answer, but you know, sometimes it's not nice to have an actual polynomial as opposed to something written in terms of sequence, right? Yeah. And if you look at the preprint that we have all on the archive, someone most recently print, we give an example of what the point cloud looks like, some explicit polynomial over there. Yeah, other questions?
This vague conjecture applies equally well in type A on other types.
Yes, yeah,
It's just the counting is hard.
yeah, the counting becomes more delicate, yeah. And in particular, the type of answer you get in type A, Ausel, Viegas, Melich, Schiffman were able to reinterpret their point count in terms of McDonald polynomials.
Right.
They were able to connect it to the McDonald work, but beyond type A, we can do the count, but it doesn't seem to be corresponding to these well-known McDonald polynomials, or you know, so they're more mysterious, the end result.
Mm-hmm. Okay.
Okay. So let me
It's 11:37.
okay, so let me before the break just talk a little bit about the additive analog of character variety as well. So what do I mean by the additive analog? Additive character variety. So by additive I mean we work with the Lie algebra instead of the Lie group. Okay, and instead of fixing conjugacy classes, we fix G orbits in the Lie algebra. And then the additive character variety is defined as follows. Defined like this. We take very similar looking data, satisfying very similar looking conditions, but everywhere group multiplication is replaced by addition in the Lie algebra. Okay? So sorry, there's two G's. One is the frac G, which is the algebra, one is the genus. Not my fault. It is G for both of them. Okay. And then we have to also divide by G, of course. And similar to before, we make generic choices for these actions, so easier to analyze. So let me denote this by y d sigma, differentiated with x g sigma. Okay, so how to think about this space? What is this space? This is actually the space of connections. This is space of connections. Of course, isomorphism classes of connections on the trivial bundle. On the trivial bundle. That's not hard to see. And remember, this is actually isomorphic to space of connections on all G bundles. So this is a space of connections on the trivial G bundle on sigma. So this is actually in some sense open part of the DRAM moduli space. So it is open inside what I denoted by M DRAM, which is the space of all connections on the bundle. And so what's the significance of this? So the significance, but there's twofold. So first of all, actually, this is what I learned from a paper of Travis, is that the singularities of this space are modeled by singularities of this space. I don't know what's the precise statement, but the singularities of the two are closely related. And this is, of course, one would expect is easier to handle because it's the algebra versus group, right? So, similarity of y and x are closely related. And sort of leave it going like that. And second thing is that with respect to the cohomology, it is expected that this captures the pure part of cohomology of that. So let me write down what that means. So expectation you look at cohomology of this. So expectation is that actually this is pure. I will talk more about what it means in a second, but it's pure and cohomology of y equals pure part of cohomology of x. What does this mean? Anytime you have a smooth algebraic variety or a smooth orbifold, you can, what does pure part be? You can embed your x into a compactification, into a smooth compactification or orbifold compactification. And then if you have a compact manifold, its cohomology is pure by their conjecture. And then, so this has, so you get a map from this here, and the pure part, when you write it here, and this is defined to be the image of this map. Let's call this map on top. So it's the part of the cohomology of x that behaves like a cohomology of a smooth projective line or a smooth projective orbital. Okay.
It is like the weight k part on HK or
Weight k part on HK. Yes.
no.
Yes. Yeah, it's the pure part. Yeah.
Why is this the space of connections on the trivial bundle? I
yeah.
actually didn't think of the additive character variety as an open subset of the multiplicative one.
Yeah,
Rather
so
being
because you
related
can
by
have-
some exponential math, things like that.
Yeah. Sorry. Sorry. Thank you. There should be actually an important addition here. If genus is 0. Yeah. E equals 0. Then this is the space of connection. So why is that? So suppose you have a bunch of elements in the algebra that add up to 0. I'm going to build the connection out of that. Okay. So the connection is going to be this on the trivial bundle. It's a Fuchsian connection, and it looks like this. You do dz over z minus zi. Okay. So this is a connection on the trivial bundle, defined by this tuple zi. Okay. Sorry, no, I made a mistake. Hold on. I need to. That's okay. I need to do that. Sorry. Fix this. I need to put a singularity. So, sorry. Let me pick points on my surface. So let's sigma 1, sigma n, the points on the surface. Then I need to put singularities at these points,
yeah.
right? And the singularity is given by the z1 to zi. So, what's a good way to write that?
Have like some zi over. So z is the coordinate now. The confusing thing is that z was also used for the elements of
yeah, that's a bad notation. Sorry.
So Probably you need to use a different notation for one or the other.
We can use T for coordinate. How
Yeah,
about
you
that?
can do dt.
Yeah, and we can call this T1 to Tn.
Yeah,
Okay,
you have zi over t minus ti or something like that.
yeah, there we go. I think that's,
Mm-hmm.
yeah, does that make sense?
Yes.
5 Yeah. So this is, by the way, sometimes called the open Durand space, because of its being open in the for instance, it's called this in a paper of Wong.
So if genus is greater than 0, this doesn't work then.
If genus is greater than 0, this direct connection is lost. Nonetheless, it's believed that that there is a relationship between the cohomology of the two spaces. Yeah.
Yes, bien sûr, in genus 0, it's a connected component, but like for your genus, it's a
I don't know in general G if there's any direct relationship between the additive versus. On the other hand, I think these singularities you say in your paper holds for any G, like that they should be.
Yes, well, there's this isosingularity theorem we're thinking about by Simpson, but I think this was for the closed surface. I'm not sure.
Okay, maybe if you put puncture, then there's yeah, one needs to be harder. That's why I say closely related, so it's not literally the same maybe for the.
Also, I don't remember if that was for arbitrary group G, so I have to check this.
Yeah.
So the isosingularity theorem. Yes, I have to check that.
But then you also say one further thing here is that if G equals to GLN, and then we're going to stop for lunch, we can restart a bit later, so we have enough time to get lunch, etc.
Yeah, we will have time.
So let me just say one more thing, which relates to the Katz polynomial, and that comes from this additive characterizing. So let me write the third significance of this space is that if you look at G equals to GLN, then if you count points of this over finite field, you discover that this is actually the same as, well, this is a theorem. This is the same as the number of absolutely indecomposable representations of the common shape quiver, which looks like this. So this is G loops here, and then bunch of. So this is the common shape quiver. So this follows from a sort of beautiful result of Crowley-Bowlby, which relates the two sides together. So this is essentially Crowley-Bowlby. And what it means is that, so what this is for GLN. So what it means for general G is that, you know, if you look at this object for general G, then perhaps one can think of that as a version of Katz polynomial, but for this quiver, but for a reductive loop. So thus, and in fact, we do show that this is a polynomial. That's one of our main results. And so this is a bit of foreshadowing, because one can think of as a deductive analog of Katz's polynomial. Katz's polynomial is exactly number of absolutely indecomposable representations of quivers. That's the definition. So Katz actually showed that this number is a polynomial and conjectured that it has positive coefficients. And this conjecture somehow gave rise to huge amount of beautiful maths related to canonical bases. It was open for 30 or 40 years eventually was proved first by, in some cases, in the so-called indivisible case by Crowley-Bowlby and Vandenberg, and then later for general by Algebra, Viegas, and Letelier. So maybe what I want to emphasize is that actually this kind of quiver is as hard as it gets for Cat's polynomial business. So once you understand Cat's polynomial for this quiver, then actually the techniques they use also work for general. So this is not like an easy quiver. Okay, it's a wild quiver. So here what we're doing is we're sort of giving an analog of Cat's polynomials for these wild quivers, but these Cat's polynomials are now labeled by reductive groups, not just GLM. Okay. So that's what I wanted to say here. Any questions or comments before the break?
What's the precise definition for column shape quiver?
Yeah, so you put a whole bunch of loops here, and then the rest is just a bunch of legs coming out.
It doesn't depend on their length, right?
So the length of these legs depends on the conjugate classes we choose, and like in GLM the conjugate class gives you a partition, and the length depends on this part. Yeah.
Yeah, exactly. So I think each leg corresponds to one of the points, right? So each leg
corresponds to one of
describes, and it's not just the length of the leg. The length of the leg has something to do with the Jordan blocks you have for that conjugate class.
But you also need a dimension
and then you have also a so if you want to allow arbitrary g-orbit in here, then you can also have some parameter. So you get this quiver, and then you get, and Crowley-Bowlby defines this these parameters on it, so that you can identify this moduli space with a certain quiver variety, not getting a quiver variety.
Yes.
Does this correspond to the consensus theories?
To the
Consensus theories, the star-shaped quivers as studied by this firm others.
It might be related.
I don't know.
Do you know the answer?
Might be related to that. I mean,
The star-shaped structure, the central quiver there.
so the star shape would be the
Genus zero.
genus zero is the star shape.
Yeah.
Exactly. So all of these things, if
But all
they,
those things are generalized, like.
yeah, I'm not familiar with this work by Ditzler, but if it's related to what you would call, the Higgs branch variety for this quiver, then it's that's what's being considered here as well.
Yeah, we calculate it, right.
So it's not literally the same when you use the multiplicative quiver variety, but the additive quiver variety, it turns out this relation you have here is exactly can be identified with the relations for the Nakajima quiver variety, for the Higgs branch variety. So this is how Crowley-Bowlby gets his results. But then these monodromy classes, OI, get translated into what the legs are, so how long they are, and what parameters you put into points to the definition.
Yeah, but that's the classic star shapes that discuss that.
Yeah, these are all stars, all possible stars.
It takes all possible G.
Okay, yeah, then that's
studies, A, B, C, D, for starters, and it takes on twisted.
if you're talking about A, B, C, D, then that might be something else. So here we're in Crowley-Bowlby, he's looking at just GLN, the group.
Yeah, so it's basically the fact it's an A type, and then you propose conjugacy, like say the each leg is associated with conjugacy class.
Yeah.
Structure has a non-polar Jews or canon.
Right, so it's a way of, so for the Crowley-Bowlby it's GLN, but he's looking at a translation between this additive character variety being isomorphic to some Higgs branch, but that for the he was doing the case with no loops originally, just the star shape.
Yeah.
So, shall we take a break?
Yeah. So So, any other questions? We're going to have time for more questions, and we're going to learn more about this after the break. But let's thank Masoud for talking. So everybody can go get their lunch and bring it back. We have the room until 1 o'clock. So. All right, so I don't see any participants online, but that's okay. Okay, so we are now going to resume our talk with Masoud Kamgarpour, speaking about Kapp's polynomials for reductive groups.
Okay, thank you for coming back. Here's our main result, which is due to for G equals GLM. It was also collaborators with this, and we did this for general reductive group. So, so the first thing is that this character variety is if you look at its FQ points, then this is the polynomial Q. In Q. And moreover, this polynomial is palindromic. So what that means is that if you read it from left to right, it's the same as reading from right to coefficients. That's what palindromic means. And this is actually an indication for indication that there is a what's called a curious. So this palindromicity is a numerical indication of a kind of a Poincare duality. But it's sort of a version of a mixed version of Poincare duality, which is called curious Poincare duality, which is known for GLN, but not for general G. And this Poincare duality in the case of GLN is explained by People's W conjecture. So this is another sort of let me say People's W phenomenon for general G. So you can think of this as a numerical palindromicity, a numerical indication of these deeper geometry.
The point is that because this is not a closed manifold,
Exactly.
it wouldn't normally have this palindromic property.
Yes, and the palindromic property, I emphasize it's curious, which means that it should be interpreted in the mixed setting. Okay, so because the cohomology is not, it's not compact manifold, so it's not the usual Poincare duality, but it's a mixed version of that.
I see.
Yeah,
Okay.
and let me also state that a second result is that the additive analog. Remember, this is the multiplicative character variety, or if you wish, a multiplicative variety, and this is the additive one. So this is a polynomial in Q as well. And then we ran a computer program on these polynomials, and we were able, whatever we computed always had positive coefficients. Okay, so this is the conjecture, which is supported by a lot of this has so conjecture Y is pure. So this polynomial and polynomial. Oh, non-negative. Okay. And for GLN, this was proved. Now, how is it proved for GLN? I'll come back to a point you made about calculus. For GLN, this was proved using the connection to quiver varieties. So one then has to show that the quiver variety associated to, these representations of this quiver is pure. And then when you look at representation of quiver, you have lots of GLNs sitting on different, for each of the nodes, you have a GLV, right? So then there's interesting characters there that you can play with to build your GIT. Here, there's no connection anymore to direct connection to quiver varieties. So we don't know yet how to prove this purity. We believe it's true, and so computer experiments seem to suggest that it's true, but it's still an open conjecture.
But yes, for GLN, like at the end, like it was going down to like there is some enough integrity, or
Can you repeat the question, please?
like for the GLN case, so at the end, like this positivity, so it was like linked with the Davison Maynard integrality.
Maynard integrality.
Like because I think that like to prove like the positivity of polynomial, they related like to like the topology of the pre-projective
Yes.
quiver.
Yes.
And after like the inequality was proven like Davison Maynard.
What do you mean by integrality?
Like the story that the interpretation of like all this also like the DPS story
It's
exponential.
chronological integrality.
Yeah. That's a little bit
That's a new proof of that. There's a new proof of this for GLN using cohomological integrality.
Okay, so it was
But the original one, which goes back to probably Bobby van der Berg, was by using twisted GIT.
okay.
Yeah, that's
So like I know that so Ben Davison like
yeah. You can also prove it using cohomological integrality.
because they are working on like reductive version for general reductive group of this conjugate inequality.
Yes, but we cannot still get this because I talked with Lucian. Yeah, and I asked him, does your result give this? But yeah,
For the GLN case, it does give it.
It does give it for GLN.
For a general group, it doesn't, but
No.
they have some cohomological.
It does give it for no puncture case. If there's no puncture,
Okay.
the result gives that is pure, even though it's actually very singular. Not smooth and very singular, but for the stack, they look at the stack and
Yes.
his new paper proved that this the stack, the additive character stack with no puncture. Yeah.
But I know that there is like I think that Ben is working also with like other people on that.
Yeah.
Like some big work.
Yeah, I mean, this is fast moving, so I mean,
So the
what
Hodge,
I knew 2 weeks ago maybe already too late, but that's what I know.
the Hodge structure is pure, you're saying.
Yeah,
Normally, you don't expect this for, these are neither smooth nor projective, but
yeah.
the Hodge structure is pure anyway.
Yes, that's the expectation. Because
And
the
that's proven
polynomial for GLN is proven.
But
In the GLN case, by the way, it is smooth. In the non-GLN case, it has orbifold singularity, but orbifold singularity is not important for purity. But you might as well think it's smooth. For instance, the compact orbifold is pure.
But in the GLN case, normally what I'm thinking of isn't smooth, so why?
Well, because we have punctures, so we put generic things at the puncture, so it will be smooth. If you remove the generic, the no puncture case, that's not smooth. Yeah.
That's right. Even with the punctures, if you don't have generic choice.
Yeah, then it's not smooth. Then the right thing to take is the character stack really, from this sort of point of view. The variety becomes really hard to, for instance, count points on because the orbit space becomes complicated.
You can have some unusual choice of partitions that for particular length, particular dimension vectors on the lens. It could be that even for generic parameters, it's not smooth. But for generic, yeah, so I guess And there's some, I guess when you say generic monodromy, you don't mean that you want all the monodromy to be just, you know,
No,
the generic,
no, it has to be
orbit.
generic with respect to each other. You know, the tuple has to be generic.
right, but when you say generic, it's not requiring that each of the monodromies is a regular conic
No.
sequence or something.
That's not enough.
That's
regular
not
is
enough,
not-
but I mean, you're requiring that. then.
No, well, we don't have to require that. That's neither necessary nor sufficient in GLA. Yeah.
So when you say generic, you have a very particular meaning. Is it exactly that this is smooth? Or what's
In the
it?
GLN case, I can tell you what generic means. In general, I can say, okay, so
Uh-huh.
generic means the following, it's like, here's one version of generic, so like, if you have, well, let's take these orbits, right?
Mhm.
This is generic. If, and let's assume this is, okay, actually, we don't even need to assume that it's, if, whenever there exists a proper
Oh.
parabolic,
We might have to get going soon.
I
Oh, no, not yet, not yet. We still have time.
there is a proper parabolic P. Is not in,
Ah,
um,
okay.
so that's,
So that's the definition of generic, and this implies that it's smooth or only in the GLN
in
case?
the GLN case, smooth, in the general case, it has finite stabilizer, so it's a smooth orbital. In the
Ah.
GLN case, it's a smooth variety.
This condition is equivalent to having finite stabilizers, which in the GLN case implies actually trivial.
Of course, it's equivalent being blocked.
Implies having
When
finite.
you have no punctures, like it's generic.
No puncture is the farthest from generic. No puncture is the most non-generic case.
Okay.
Yeah.
Okay, so you really like need to have like some punctures.
Yeah, I mean, the whole point was that introducing these punctures makes things easier, actually. Provided you put in,
But generic is not equivalent to saying, for example, that that everything. Yeah, that, you know, like for stability conditions, semi-stable equals stable. So here, you don't have a stability condition. So just saying that
well, this implies that
everything is
G acting on this, the semi-stable points equal stable.
right.
Whenever you have a finite stabilizer, that's implied.
Right. In this case, there's no stability condition, but nonetheless, you can make sense of this.
The stability condition with the trivial character.
Right.
It's still a condition, but it's just, yeah.
Stability of the.
like, it's still, we have an action of G on an affine variety, we can use the trivial character and talk about when things are stable or not. Yeah,
So that, but generic means that.
implies that stability equals things.
Normally, I think that's the definition of generic first.
Yeah, it might be equivalent, I just don't know that,
You want this to be your definition, whether or not that's a good.
yeah, because this definition is least theoretic.
Okay.
You know, I'm not 100% sure if it's equivalent to that,
Semi-stable
geometric.
equals stable.
yeah.
Okay.
For example, like you have a story of like for the reductive algebra that you can form like the deformed instead of deformed reductive algebra.
Yeah,
But the idea is that this deformed reductive algebra, it means that at the end like you have a hypercalaire quotient, you will just have
exactly, at the end you have a what?
A hypercube.
Yeah.
But like here, like
Yeah,
here,
that
like some
becomes
hyper-
part of- yeah. Yeah,
that-
this deformation space is, I don't know how to, yeah.
Yeah, like
As I
that.
said, that's
They should have a hypercube structure on the smooth locus also, right, for any.
in the multiplicative case, in the additive case.
I would think
Yeah,
that is still
probably,
given
but I
by a
haven't thought about
hypercube
it.
quotient, so therefore it should have a hypercube structure.
Yeah, hypercube quotient, yeah, on the smooth part, yeah, I think actually it does, yeah.
But the
Um,
singularities will be more complicated for G naught type A.
Yeah.
Also, so like for general like reductive group, so you have like a minimal number of punctures, such as you can have like generic.
If your genus is bigger than one, bigger than equal to one, as soon as you have put one puncture, you can make things generic.
Okay, so it's you want.
If the genus is zero, then you need 3 punctures to get something
Right.
interesting. That's
Exactly, and for genus 2 or bigger, you don't need any functions.
to make what?
Um, Well, you wouldn't need any
Yes,
functions.
and so it's really a story like a story of stable curve.
You have finite automorphism group.
Yes.
Everywhere.
Yes, it's a question.
No, I mean, there's open dense that has finite automorphism group, but yeah,
Like it's really related like to yes, to the question of stable curve.
yeah. By the way, so maybe another open question is, which one of these, when we put in the punctures, where do we have, for instance, symplectic singularities? I think you guys worked on this when there was no puncture. But maybe not with the puncture or for general G.
With the puncture for the the GLN case, we yeah, then we could say there's symplectic singularities for both the additive and the multiplicative. But for general G, I guess I mean, it looks like it's going to be a symplectic quotient, a Hamiltonian reduction, or like a hyperkähler quotient, so then that should imply probably that it has symplectic singularities, but one has to be a little.
Yeah, we can talk about it. Yeah,
But
yeah, so but maybe we have to go, right? Probably that's.
we have a few more minutes. What else did you want to tell us?
Well, I mean, the rest would have been talking about the proof, which I don't want to get into. Like, how do you actually count points? I mean, maybe I just say a word, is that there's a formula for medius that reduces counting points to representations of finite groups, finite reductive groups over complex numbers. So,
So you're gonna tell us how you can count the points, is that what?
and then we use the linguistic theory to count points. And that's why actually I gave this to my students to work on, because finite groups are a bit more accessible for students. So they were mostly sort of playing around with the linguistic theory and learning the basics of it to
But
count
the
points.
linguistic theory is not so easy to learn, though. Is it?
I mean, we needed some results from there, which we could take as black box. They didn't have to learn, for instance, homology. We could use the theorems as black box.
Okay.
Yeah. And maybe another sort of fun fact is that if you take, we want just to show you how broad this is. If you take just G to be, instead of reductive, take it to be the unipotent group, unipotent upper triangular. Triangular. And take a genus, which is B1, and look at the character variety associated with this. So that's the space of commuting matrices in here. So XG sigma is the commuting variety, or maybe the stack version, stack version. So it's A, B in ULN that commutes. Okay. And this, so the conjecture is that this is also a polynomial in Q. And this is a reformulation of a famous conjecture of Hickman from 1960. That because actually one can show that this is the same as the number of conjugacy classes, essentially up to a factor of size of the group of this group over finite field. And Hickman conjecture is that this is a polynomial in Q. And this conjecture has driven a lot of people crazy trying to prove or disprove it. And it's still open.
What does this have to do with the rest of your circuits? This is a non-reductive group.
Yeah, I'm just saying that this is sort of fun fact that for the reductive thing, we have all this structure of the linguistic, etc., which allows us to compute things. Whereas when you go to the unipotent case, like there's interesting open questions of the similar flavor, but we don't have the techniques to we don't have enough structure in the unipotent case to.
Does that result like that in the nilpotent case? But it's not in the.
I think there's also similar thing in the important case. Yeah.
Whatever I was thinking that there were formula for the continued stack. It's a nilpotent case.
I think there's
a.
Yeah, so he talks about this conjecture explicitly and relates it to his thing,
So
but it's still not resolved.
What's the general statement? So if you want to count points of X, so you want to count points of Y, then can be done using finite groups and
Oh, yeah, I can write it down.
so some theorem you prove for general G,
Actually, theorem of Frobenius.
for BDS.
So let me, actually, this is a really cool theorem of Frobenius, which should be in every representation theory course,
Sure.
but it's not. So the result is this. If you want
I
to.
just finished teaching representation theory after 7 years, so I don't know. I can't add it now.
So the result is if G is a finite group. So in our application, G will be G of Q.
Mhm.
And suppose you want to know the number of solutions to the following equation in G. So you want x1, y1.
Sounds similar to the things that Martin Liebeck was working on.
Yes, I've actually used these papers. Or yeah, if you want to know these in, and let's take some conjugacy classes in G. So 1 to 10. So this, the number of such things equals the sum over irreducible characters of G. Irreducible complex characters. Then you have to do order of G divided by the dimension of these, and then product IN, IOR. So this is the representation theoretic. This number is G times this. Okay. So it's telling you, this is one of the first applications of representation theory to group theory. This is a purely group theoretic question. How many solutions does this equation have in a finite group?
Right.
And Frobenius gave a representation theoretic answer.
This is used by these guys, Hausel, Rodriguez,
Yes.
etc.
Yeah, they use it for GLFQ and we use it for general G. Yeah.
Yeah.
Let's
Great.
say you don't divide by the lambda in this case.
Yeah, no, we're dividing by G, you see? Because this is, yeah, yeah, it's finite group and it's, yeah.
Okay. Well, let's thank Masoud. So we can move to my office now, I think. We can continue discussion.
Should I raise the box?
That would be nice, yeah.